Okay. Hi everyone. Today we're starting to show you our smart launch system. Before that, here's our group member and and a project that we have been built across 3 labs. It started with simple, but now we can it can detect, introduce, sun alarms and even log door automatically. In lab 3, we build a core system security keypad that disarms the alarm with an OLED display showing status. Then in lab 4, we add a motion detection using a PIR sensor and allow buzzer alarm. Finally, in lab 5, we integrate a servo motion model that physically locks the door when alarm. And the magic behind it all is free RTOS. Instead of one chunky program, we split everything into a specific text, one for the keypad, another one for motion detection, and so on. This means when someone moves, the alarm triggers triggers instantly without waiting for other process. They so it isn't just work. It work like a commercial system. The motion sensor detect reliably and the log engage, uh, and the whole system respond in real time. Okay, let's show you how it works and begin with the more detail.
For our labs this semester, we use the STM32 Nucleo board as our main controller running FreeRTOS. It provides GPIO pins, timers, and communication interfaces including UART, I2C, and SPI. We had numerous peripherals connected to the STM32 Nucleo through a breadboard. These included a 4x4 keypad, an OLED screen, a PIR infrared sensor, a buzzer, an SG90 servo motor, and numerous LEDs. First, the 4x4 keypad is represented by a matrix of 16 keys, which are arranged into 4 rows and 4 columns. The keypad is used to enter the passcode to arm and disarm the system. The STM32 scans the rows and columns to detect which key the user pressed. Another component that we used was the OLED graphical display, which communicates out over I2C. The OLED display user prompts for users to enter a code, whether the system is armed or disarmed, and general feedback on the system status. We also used a motion sensor to detect infrared radiation changes, which indicate movement. When armed, this PIR sensor detects motion and then triggers an alarm. We have a buzzer that we use in our system that produces an audible tone. It is activated when the system is armed and the PIR sensor detects motion. This buzzer is driven by a GPIO pin, which is either set to high or low. We have a few basic LEDs connected to GPIO pins that provide a visual indication of the system status. If the LED is green, that would indicate that the system is not armed, and if the LED is red, then the system is armed. We finally implemented a small servo that simulates a locking mechanism. When armed, the servo rotates 90 degrees to indicate that the system is locked, and when it is disarmed, it returns to 0 degrees, indicating that the system is unlocked. In our alarm system, we have 4 tasks running in parallel. The first task is called the default task, and its purpose is to toggle the red and green LEDs between their high and low statuses. This depends on the armed status of the system. In lab5, we expanded the default task to also include the servo functionality, which rotates 90 degrees when the system is armed, and back to 0 degrees when the system is unarmed. The second task controls keypad input and OLED display. This task is called Task 2. In this task, we initially wait for user input on the keypad, which is then compared to a stored password. If these passwords match, the system is disarmed and the user is prompted to enter a new password moving forward. If the passwords did not match, the OLED displays wrong code and the user is prompted to attempt again. The third task controls the buzzer. This is called Task 3. In Task 3, we wait 1 second initially and then check whether the system is armed. If so, we check if the motion sensor has been triggered. If so, then we turn on the buzzer. If the system was not armed or the motion sensor was not activated, then the buzzer is set to low. Our final task controls the motion sensor. We called this task Task 4. Similarly to the last task, we initially wait 1 second before we check the system status to see if it is armed. If it is, then we read the value from the motion sensor. If the motion sensor detected something, then we set the flag sensor triggered to true. If nothing is detected, then we set the sensor triggered to false.
Okay, so here it all is. We're going to enter the code 1111. Not armed. We're going to enter the code. We're going to put our hand here. There we go. Still going. Back to normal. Wrong code. Once again, the same process. It's hypersensitive, so it'd probably write it again, but now it'll do the same process.
So for the performance analysis and feature improvement, like we saw in the video that we just showcased, in our system, we successfully integrated the 404 keypad, the LCD display, the PR motion sensor, the buzzer, and the servo motors using the free RTOS and STM32 Nucleo display. So our implementation ensure real-time task scheduling, secure input handling, and proper system state transition between armed and unarmed. However, we identify some performance issue that we had during our testing that could potentially be improved in the future if we were to make another implementation of it. So one of the major challenges was task synchronization. The FreeAutoTOS allowed us to run separate tasks for the keypad, LCD screen, and the alarm system. And there was some delay inconsistency. So, for example, in the keypad, we would, let's say, put a number, and it would take time for it to load in the screen. And there is some of the delays that we face, which we managed to fix, but it was something that became a little bit inconsistent. And also the buzzer, for example, sometime was not triggered at the expected time. And I think one of the issue for that was the motion sensor wasn't detecting wasn't working properly. So when there was a motion, sometimes it would detect it, sometimes it wouldn't detect. And I think in the video, uh, it can be seen. Um, so to adjust this, I think in the future implementation, we can adjust the task priorities or implement like some interrupt-based activation system instead of relying solely on. I think we use a polling method to implement this. So I think that would be something that we'll have to do in the future. So another improvement would be the servo motor control. So right now the motor engages when the alarm is triggered, and then afterward, which triggered the locking mechanism for the servo, which represent the door. But we did notice some jitter in the movement, but I think that might be the servo itself, but that could be something that we could look at and make sure that it wasn't it's consistent. I don't think in our video it was shown, but that might have been just the show, but that is something we should look at. um, Also, as I talked before, the motion sensor sensitivity is sometime it would we had a putty where it shows the value that it gotten, so one and zeros, and really was really inconsistent, and so we had to switch other motion sensors many times, and we sometimes we had some that were more sensible, and so maybe if we had more time to properly look at it and see how it would work, to have it in an environment where it would work consistently, that would be pretty good. Um, and I think lastly, um, I think that should be good. Maybe if we add the light, maybe some flashing light just to give more indication. But I think for most part, that would be the changes that we would add for our motion sensor for the implementation. So to conclude, this project successfully combined hardware interfacing, embedded system programming, and real-time task management to build a functional alarm system. When we starting from lab 3, we interfaced the keypad and LCD display so that we could know how to handle secure user input and use 12C communication for display updates. Then in lab 5, we completed the system by integrating the servo motors using FreeRTOS, ensuring that all the components work together efficiently. And of course, in lab 4, we did implement the buzzer, which worked. But now we in this lab, we had a chance to kind of improve the system. We A key takeaway from this project was task scheduling in real-time system. We moved from a basic super loop approach to a task-based FreeRTOS implementation, improving system efficiency, which this experience reinforced our understanding of communication, peripheral communication, GPIO handling, and FreeRTOS task management, and really gave us a detail into how we could implement everything. And so and this we also encountered and overcame hardware challenges, which were a lot of main issue that we had, and then synchronization was another, such as debugging, unresponsive keypad, inconsistent buzzer behavior, and power related LCD failures. We had to change some LCD, the LCD screen a lot of the time. And so these challenges actually pushed us to explore better debugging techniques and hardware troubleshooting, where we had to implement PuTTY, track the keypad display, same for the buzzer, and of course for the sensor. I think that was one of our most difficult one to actually know how it worked. Which at the end of the day, it was a very troublesome hard work. In the future, for improvement, we it would be we could implement better task synchronization, enhance LCD prompts, optimize servo control, and possibly a silent alarm mode that could be cool to add. That could make the system more robust and actually make sure that it serves properly as an alarm system. This project, of course, has provided all of us valuable hands-on experience in real-time embedded systems, preparing us for more advanced application in security and automation, which really showed us how all the system work together and how every component work on top of each other, which I think this lab really helped us understand, since you can't do one lab without doing the previous one. And I think that if one didn't work, which we face a lot of issue, especially in our lab 4, where some LEDs wasn't working, but this really helped us understand how these systems are implemented and how they're built upon each other, like one task at a time. Overall, this project was a great learning experience, demonstrating the importance of integrating hardware and software in real-time system while addressing real-world constraint like task execution, timing, and resource management.